she was in her 40s.
Okay, my mic should be working now. Kind of a dead intro there. So welcome everybody. I'm not even on the right screen. So this is 112 live. So we're going to go ahead and jump into chapter 7 here. Okay. So essentially what we're doing here today is we're going to talk about how to add numbers together, how to multiply numbers together if they're in a different number system. Okay? So as you know, it's one thing to count events, which we'll do with chapter 10 and chapter 12, where we set up these counters to count things that happen. But what if you wanted to take two binary numbers, and add them together? Okay? So we're going to spend a little bit of time on just the arithmetic part, and then we're going to talk about how to create these circuits in digital logic. Okay? And then, as with everything, there's an IC for that, and we'll talk about those later as well. Okay? So, in binary arithmetic, the first three here, really all of these hold true, right? Not hold true, but you recognize them because this is how we would do this in regular addition, right? 0 plus 0 is 0 carries 0. 0 plus 1 is 1. We don't carry anything to the next column. 1 plus 0 equals 1, carried 0 to the next column. This is where it gets a little bit different, right? Because 1 plus 1 does not equal 0, it equals 2. But think about what the number 2 is in binary. It's 1, 0, right? So if you're saying 1 plus 1, then you're saying 1 plus 1 equals 2, right? If we're talking about in binary. So you can see here, 1 plus 1 is 0 in this first column, and then you carry 1 to the next column. Right? So it's the same addition as decimal addition. It's just that, you have to change over every time you get a 1 plus 1. All right? So here we go. And here's how you could say this. You could say that, here's the summation and then the carryout. Right? Here's the summation number, digit, I guess, in this case, and then the carryout. And so there's only one in the addition. Okay? And that's just two binary digits added together. We're also going to look at what happens when you have three of them. Okay? And so here we have two binary numbers, and these are binary digits, A0 and A1 and B1 and B0. Okay? But we also have this third column now that we have to consider because we're carrying in from the previous column, right? Just like we did in second grade when we started learning how to do this stuff. So the summation and the carryout are the same as this right here, okay? But now we have to take into account this last section here, or this last case, where potentially A1 and B1 are both 1, but then you also have a carry-in. See what happens here. So now the summation is 1 and carry the 1, because what is 1 plus 1 plus 1? It's 3. And how do we represent 3 in binary? 1, 1, okay? So all of the rest of this follows this truth table right here. All of this follows that truth table except for the very last one because you've got 3 ones that you have to consider. Okay? But you can see in all the other ones, just take this one right here, 0, 1, 1. So 1 plus 1 is 2, right? So that's 0 and carry the 1. If you're going to subtract, the same things apply, except this time when we borrow, right, I guess we'll look at the other cases first. This is the same as regular addition. This is the same as regular addition. This is the same as regular addition, right? You're not borrowing anything because I can't ever remember the name of the two. We always remember denominator and numerator for division. But the first part of the subtraction is called something, and the second part of the subtraction is called something. Okay, and gosh, I'm going to look it up real quick. So subtraction terms. It's like subtrahend and the... Okay, so the terms of subtraction are called the minuend and the subtrahend. The outcome is called the difference. The minuend is the first number. It is the number from which you take something, and it must be the larger number. Well, unless you get a negative, right? Oh, come on. Now Mozilla wants to quit on me. Don't do this now. Oh, that's just great. Okay. All right. So the minuend from the subtrahend from the minuend. Those aren't terms that we use all the time, but anyway, when the second number is bigger, obviously this creates a well, in our case, if we were going to use decimal, we would borrow from the next column. We would borrow 10. Well, because each place does not represent 10, we would borrow 1, because that's the only thing that we can borrow from the next column, right? So that looks like this, right? And the reason why this happens is because the second number is bigger than the first number, okay? And that's the only situation really that's kind of funky. So you can do the subtraction like this. We're gonna use a different method to solve the subtraction, so I'm not going to go through this a whole lot, but it's the same thing, right? A sub 0 minus B sub 0, whatever the remainder is, and then do you need to borrow from the next column, okay? Multiplication is, I think addition and multiplication are the easiest of all these to do. And even the long division is not too bad. But you do binary arithmetic exactly the same way that you would do regular multiplication with decimal numbers. Okay? Whoops. So it says, multiply the first bit, the least significant bit of the multiplier times the multiplicand, the whole thing. And then you move over and you shift the result. Okay, I'm going to do a few of these on the board. But here you go. Here's 13 times 11. If you did that with decimal, you come up with 143. All right? And so this is a pretty boring, because it's all either ones or zeros, right? And so if you take the bottom times the top, we start with this 1, right? So 1 times 1 is 1. 1 times 0 is 0. Basically, you're going to rewrite this whole thing on every line that's got a 1, right? So I rewrite the whole top because it's times 1. Then I shift over, if you remember this, and then I do the same thing. The second one is a 1, so it's 1 times 1, and 1 times 0, 1 times 1, 1 times 1, 1 times 0, all the way down. Okay? The next one, we shift it over. It's all zeros, right? Because there's a 0 here. So 0 times 1 is 0. 0 times 0 is 0. So that whole thing gets blanked out. The next one is the last one we really need to worry about here. And again, it's 1 times 1, and 1 times 0, 1 times 1, 1 times 1. So all of that gets printed out here. And remember, each one of these you shift over. That's how you shift this over. And then you add everything together. You add all the columns together. And then here's what you come up with. So the method, the way it looks, is exactly the same as when you would multiply two decimal numbers together. Okay, same thing here, right? You take the first number, which is a 1. 1 times 3, 1 times 1. And then you shift over, and then it's 1 times 3, 1 times 1. And then you add them all together. 3 plus 0 is 3. 1 plus 3 is 4. 0 plus 1 is 1. Okay, any questions on this? I'll have to pull this back up since it quit working on me. Okay, so I just pulled my Firefox back up. Did it continue to stream for the last couple minutes? I assume since you're all here that it's still streaming. I just couldn't see it up here in my YouTube. Okay. Okay, good. Thank you. Okay, so for division, same as decimal division. We're going to go back to the second grade yet again and do long division. So in long division, you set up this radical, right? That's what we call it. And you take the denominator into the numerator. So in the first one, it's 9 divided by 3, so we take 3 into 9. How many times does 3 go into 9? It goes 3 times. 3 times 3 is 9. Subtract the bottom from the top, you get 0. Okay? Same thing if you were going to take 3 into 9. Binary 3 into binary 9. Okay? And the way I would do it is like this. I would say, how many times does 1, 1 go into 1? 0 times. How many times does 1, 1 go into 1, 0? Well, 0 times. How many times does 1, 1 go into 1, 0, 0? Oh, okay, now that goes 1 time, because it only either goes 1 time or 0 times, right? It can't go into it 5 times. So put the 1 up here. Now multiply 1 times 1, 1 times 1. Subtract that from the top. So I have 1, 0, 0 minus 1, 1, which is 4 minus 3, right? Which is 1. And then again, with long division, you pull down the next available digit. And so now you say, how many times does 1, 1 go into 1, 1? Well, it goes once. Subtract that, and you get 0. Okay, so the answer is 1, 1, which is 3. So the long division is exactly the same as regular division. Okay? Now, in this case, you know, we're looking at 2 examples here where everything works out nice and neat, right? What happens if you have a remainder? Okay? In all these cases, you don't have a remainder, but it is possible that you could. Okay? Like if this was 17 into 222, well, this final thing down here, where this 1 gets pulled down, that would be a 2, and so it would be different, right? You would have a remainder off to the side here. So it is still possible to have a remainder down here. You could get down to something where you say, how many times does this go into that? Well, it goes 0 times, and then you're going to have something that's left over. Okay? So this is what we're going to use for subtraction, all right? We're actually going to use addition to do our subtraction. But to make that work, the first thing that we need to do is we need to convert the, I guess in our case it would be the subtrahend, right? The minuend is what is the bigger number, and then the subtrahend is what gets taken away from it. So we're going to take the thing that's being subtracted, and we're going to give it a 2's complement representation. So it says both positive and negative numbers can be represented. Here's something that you need to remember, right? It's always in groups of 8. You have to do groups of 8 because this leading bit here, this 8th bit, D sub 7, is always the sign bit. So that's either going to be positive or negative. And so if you just have a small number like positive 7, then it's going to be 0, 0, 0, 0, 0, 1, 1, 1. But you have to have all 8. So again, when I write this number, let's see if there's one written here. Okay, so here's the range. This is the range of the numbers. Anyway, when I do this, I'm going to put a little subscript down to the bottom right that says that it's 2's complement, okay, because it's just going to be another string of 1s and 0s potentially. And so, you know, we know that that could be a string of binary digits. It could be a BCD number, and it also could be 2's complement. So we need to, you know, denote what it is. What number system is it? Okay. So again, the sign bit is the one out in front. So really you only have 7 bits to work with, even though this is 8 bits total. The front one is always the sign bit. So that's why there's a restriction on 0 to 128 and -1 to -128. And this kind of stuff right here, I love to ask on exams. Okay, these are easy questions to ask. What's the range of an 8-bit 2's complement? What's the range of negative 8-bit 2's complement? That kind of thing. Okay. Something else I want to point out here, that the positive numbers are all the same binary numbers from 0 to 128. The only difference is you're just putting a 0 out in front of each one of those. Okay. Where it gets funky is when you have your range of negative numbers. Notice that -1 is all 1s, and that -128 is this, is 1 with a bunch of zeros behind it, okay? So it's almost kind of backwards. You might think that, you know, when you get down to 0 here, that that this might be the first one on the other side, but it's actually this one. It goes from 0, 0, 0 to all ones. Okay. I'm actually going to walk through this on the board, so I want to get down to this. Okay, and this shows you what I just said. All the positive numbers count in binary from 0 to 128. Okay, it's only when you start to go negative that it looks like it's counting backwards. The more negative you get. So you start at -1 at 1, 1, 1, 1, 1, 1, 1, 1, all the way down to, as we said, 1 and then all zeros behind it. Okay? Let's see here. I think this is just more explanation of what I'm going to show on the board. Okay, let's do this right here. It says convert the following numbers to 2's complement form. We can do that. I'm going to flip off my camera and flip it back on so that it resets the time. And now I will flip over. All right. So what we're going to do here is we're going to convert decimal value into 2's complement. And the PowerPoint example was the number -35. Okay? So the first move in converting a number to 2's complement, so the first move is to write down number in binary. Just ignore the negative sign for just a second, and I can see that it has failed to update again. Hang on one second. Switch to this. Switch to this. And now you can see what I'm doing. Okay. So, we're going to convert a negative decimal value into 2's complement notation. Okay? And again, 2's complement notation is always 2, 3, 4, 5, 6, 7, 8 bits. 8 bits, this is always the sign bit. Okay? So the number that we're going to convert is the number -35. So the first goal is to write down the number in binary. Okay, so we're going to convert 35 into binary. I'm going to go to my binary converter so I don't have to sit down at my computer, and I don't want to do it in my head. So we are going 35 from decimal to binary. And that is 1, 0, 0, 0, 1, 1. And so I'm going to put the leading zeros out in front here, okay, so that we make 8 bits with this. Okay? All right, so that's the first thing, is to write down the number in binary. The second thing to do, subtract 1. Hang on a second. Hang on 2 seconds here. Jeeps. Okay. Getting a little bit ahead of myself here. So we are going to add 1. So we take the number 0, 0, 1, 0, 0, 0, 1, 1, add 1, 1 plus 1 is 2, so that's 0, carry the 1. 1 plus 1 is 2, that's 0, carry the 1. 1 plus 0 is 1, and then the rest of these I just copy. Okay? So write down the number of binary, add 1, and the third step, invert all digits. Okay? So that means 1, 1, 0, 1, 1, 0, 1, 1. Okay? So this is the 2's complement of 35. Okay? All right, let's do another one. Okay. How about if we take, let's do something fairly easy. How about 14 minus 7? Okay? So ultimately, I'm going to do an addition between two binary numbers. I'm going to go ahead and convert 14 into binary. Okay, and I get 0, 0, 0, 0, 1, 1, 1, 0. Okay, that's my 14 in binary using all 8 bits. Okay, now for my 7 in binary, I add 1 to it. Now I know this is 8, but I'm going to walk through this. 1 plus 1 is 2. That's 0, carry the 1. 1 plus 1 is 2. That's 0, carry the 1. 1 plus 1 is 2. That's 0, carry the 1. And then I rewrite these. Okay? Now I take this and invert all of them. So I've got 1, 1, 1, 1. Okay, now that's the number I put here. 1, 1, 1, 1, 0, 1, 1, 1. Okay? So this is the 2's complement of 7. So now, instead of subtracting 7 from 14, we're adding its 2's complement to 14. Okay? So over here, 1 plus 1 is 2, carry the 1. 1 plus 1 is 3, that's 1, carry the 1. 1 plus 1 is 2, that's 0, carry the 1. 1 plus 1 is 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 0, carry. Okay, now, I've carried this out past this 8th bit, right? Just because of the way this is oriented, okay? Let's see, did I get all those? Looks like it, okay. All right, so I've added them together. If you have something that comes out here, you just ignore it. So if we do all this addition and we have something that's out here in the front, we just ignore it, okay? And then the way that we get the answer is we do the inverse of what we just did. Okay, so the last thing we did is we inverted. So now I'm going to invert all of this. So 1, 1, 1, 1, 1, 0, 1, 0. And now because here we're going to subtract 1. Let's see here. I'm missing something here. Hang on a second. Oh, I see what I did wrong. Dag nabbit. Dagnabbit. Let's do this. I got the order of the two backwards. I kept thinking there's just something not right with my. So 2's complement. And then you add. So 14 minus 7, we already said that this is 0, 0, 0, 0, 1, 1, 1, 0. Okay. And the 7 we came up with was 0, 0, 0, 0, 0, 1, 1, 1. And we go ahead and invert them all. 1, 1, 1, 1, 1, 0, 0, 0. Then we add the 1. Jeez. Okay, now we take this number and add it to the first one. Okay? That'll give us 1, 1, 1, 0, carry the 1. All of these will be 0, and then the 1 will be carried out here. Okay? Now, if you get a result from this 2's complement, 0 out in front, then that's as far as you need to go. You just do a conversion. Okay? So you may make a note here that says, if the most significant bit or the sign bit is 0 or positive after a 2's complement subtraction, do a direct convert to binary. Okay? Okay, so obviously that comes out 7 if we do a direct correlation. Let's do another one. Sorry about that. I'll cut out that first part. I wrote them in the wrong order. But really, this is the only time that we ever talk about this. We don't even really get much into it in 122 either. Okay. All right. So let's do something that's not as nice, and we can't do the direct correlation. Let's do how about 12 minus 20? Okay. So the first part here, we just directly convert that. So if I put in 12, we should get 0, 0, 0, 0, 1, 1, 0, 0. Okay, that's our binary 12, 8 plus 4. Okay, so for 20, we have 0, 0, 0, 1, 0, 1, 0, 0. Okay, so first thing we do is invert, and we get 1, 1, 1, 0, 1, 0, 1, 1. Add 1 to it. 1 plus 1 is 2, carry the 1. 1 plus 1 is 2, 0, carry the 1. 1 plus 0 is 1, and then I just write everything else down. Ooh, look at that. Okay, so those are the two. 0, 1 is 2. 1 plus 1 plus 1 is 3. Carry the 1. Right. Now, this time, okay, since MSB, or the sign bit, really, is 1 or negative, do the reverse of the 2's complement. Okay, in that order. So the first thing we do, we take 1, 1, 1, 1, 1, 0, 0, 0. We subtract 1. Okay, and so ultimately it's going to borrow from here, right? And so you're going to be left with 1, 1. and that's going to be 0, 1, 1, 1. Okay? And then we just invert them all. So this is the subtract 1 part of this, and now we're going to go back to the first part, which is invert them all, and we get 0, 0, 0, 1, 0, 0, 0. Okay? Now, because we had to go back to here, this is a negative number, and so our answer is -8 in decimal. Okay? So this is how we would express -8 in binary. We would use its 2's complement, use its 2's complement notation. Okay? So after this, like just to reiterate, if you get a positive out here, if you get a 0, do a direct correlation to binary, from binary to decimal. If you get a leading 1 out here, that means this is negative, and then you have to go in the reverse order of how you got to the 2's complement to begin with. So first thing you have to do is subtract 1, and the next thing you do is invert them all back. Okay? Any questions on this? Ah, shoot. Mike is cutting out again. Dagnabbit. See if I can tighten this up here. Stick it up on my face here. Okay. Okay, he said it wasn't too bad. Okay. It's always when I turn. I don't know what it is when I turn, but you know. Probably just need to ask the school to buy me a brand new one. And so Steve says, where is this applicable? It's applicable right here in class. Where will you use this in industry? Probably never, but this is how things are calculated. So, one of the discussions we're going to have later on today is we're going to talk about arithmetic logic units, and so that's where you see it. So if you were to go work for Intel, or if you were to go work for any other semiconductor manufacturer like that, where you're making, well, Intel makes processors, this is how information is processed in the processor, right? So there's not like a what would you say? There's no good example of, like a household item where I can show you this is being used. It's like you'd have to get inside the processor of an arithmetic logic unit that's doing all the calculations that a computer does to see how it's applicable. That's really the only place I know of, okay? But this is how the computer deals with negative numbers and deals with positive numbers, because again, it's just a dumb computer that only knows what we tell it. So, yeah, that's where you're going to find this stuff applicable. So if you are part of the team that's designing a new Intel, I-Core whatever, then this stuff is useful to you. All right. Now, like when Professor Atkins was at Intel, he wasn't sitting down doing this stuff by hand, but it's just like anything else, right? And take for instance just 111 because I know that a few of you in here, three or four of you in here are in 111 with me, right? When you get into industry, you are not going to sit down and build stuff by hand, right? We learn how to use the DMM, we learn how to use all of the equipment. However, the majority of the time, engineers spend all of their all of their development time on Multisim and other software development packages. But you still need to know how to use the equipment. You see what I mean? So it's I know that's a long answer to what seems like a simple question, but where's this applicable? Man, it's it's the heart of the device that you're using right now, right? Because as you know, or maybe you don't know this, but all of the statements that are executed by the processor that support the system, Windows or whatever, all of that stuff is just a bunch of arithmetic. It's a bunch of adding, and it's just ones and zeros. And so, like I said, it's not applicable in any tangible way, but if you were designing a chip for, say, Intel, then it would become important, even though you still wouldn't be doing this by hand, right? You have very sophisticated software that will do this for you, okay? But you'll have the advantage of being able to tell your friends that you know how to do this, and it will impress them, right? Maybe not. All right. I want to do a few more of these, and I want to do some basic arithmetic too. Let's do one of those. How about well, let's do one that'll work out nicely. How about 21 divided by 3? Okay? So, if I use my converter, because we can do that in chapter 7 now, and we're not in chapter 1 and 2 anymore, I'm going to take the number 21, convert it to binary, and I get 0. Now this time we don't need the 2's complement, so I'm just going to write 1, 0, 1, 0, 1. Okay, that's 21. The number 3 is 1, 1. All right? So how many times is 11? 11. Stop it, John. How many times does 1, 1 go into 1, 0? 0 times. How many times does 1, 1 go into 1, 0, 1? It goes once. Okay? And so that's what? 5 minus 3, you're left with 2. Bring the 0 down. How many times does 1, 1 go into 1, 0, 0? It goes once. So now we got 4 minus 3. That gives us 1. Bring down this other one. How many times does 1, 1 go into 1, 1? It goes 1 time. Okay? So how many times does 3 go into 21? It goes 7 times. Okay? All right. How about 12 times 14? Okay? So 12 is 1, 1, 0, 0, and 14 is 1, 1, 1, 0. And with multiplication, just like addition, it doesn't matter what the order is. You could flip them if you wanted to. Okay, so the first row is going to be all zeros. What's 0 times 0? It's 0. 0 times 0, 0. Boom, boom, boom. Okay, now we're going to shift over 1. Now we got 1 times all of that, so it's 0, 0, 1, 1. 1 times 0 is 0. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. Now we're going to shift over again. Okay, same thing. 0, 0, 1, 1. Shift over again for this very last one. 0, 0, 1, 1. Okay. Now if I do this one up here, I get what? 8. 48. So that should be, I think 168 should be our answer. Okay. And so now you just add everything together. So we've got 0, 0, 0, 1. 1 plus 1 is 2. That's 0, carry the 1. 1 plus 1 plus 1 is 3. That's 1, carry the 1. 1 plus 1 is 2. So here is my answer. And then I can take my my converter, 1, 0, 1, 0, 1, 0, 0, 0, convert from binary to decimal, and I get 168. Okay? Any questions on on any of this? Okay. And I'm down to 1 bar on my batteries. That's not a big deal. I think I should be okay. All right. So again, we have these great inventions called calculators that will do all these things for us. And now we even have phones that will do it for us. Okay. Let's see. Let's do another one. How let's do some bigger numbers here. How about 79 minus 100? Okay. So the first thing I'm going to do is I'm going to convert 79, and I get, let's see, I'm going to need a leading zero here, so 0, 1, 0, 0, and then 1, 1, 1, 1. Okay, so that's 79. So now I want to take 100 and convert that to its binary equivalent. And I get 1, 2, 3, 4, so 0, 1, 1, 0, 0, 1, 0, 0. Okay, so go ahead and invert it all. 1, 0, 0, 1, 1, 0, 1, 1. Add 1 to it. Carry the 1, carry the 1. Okay, so this is 1, 0, 0, 1, 1, 1, 0, 0. Now, obviously, the number we should get here is negative 21 should be the answer, okay? All right, so let's go ahead and add these together. So I've got 1, 1. 1 plus 1 is 2. That's 0. Carry the 1. That's 3. That's 1. Carry the 1. 1 plus 1 is 2. That's 0. Carry the 1. There we go. So we have a negative number because we have a 1 out in front. So now we're going to have to go the other way. So subtract 1 from this. 1, 1, 1, 0, 1, 0, 1, 0. Invert them all. 0, 0, 0, 1, 0, 1, 0, 1. And so if I go back to here and I say 1, 0, 1, 0, 1 and convert that. Whoops. The other way, I get 21. So I think we just determined that is the case. Okay. Okay. Steve says good so far. Thanks for the feedback. All right. You know, I could keep doing these over and over and over, but if you're good on this, then I'm not going to spend a whole lot of time on it because I will ask you to do some of these on the exam, but they're not going to be any harder than this, okay? So just two numbers, subtract 1. I'm probably going to make the second one bigger, or, you know, I could make it smaller, I guess. You could also have division. You could have multiplication, and that's it, okay? So I used to, you know, to get back to the PowerPoint here, I used to go into depth about hex arithmetic. Let's see if we can get down to it here, all right? But this is just, I don't know. It's very, very hard for students to do this, okay? And I understand the frustration, so I don't get it much into it. But just know that when you're doing hexadecimal arithmetic, if you're taking, you know, 12 plus 9, that's, you know, that's, it says add 9 plus C in hex. All they're doing here is taking a direct, converting C to 12 and then doing a decimal, all right? But if you were to do that in binary, right, when you borrow or, you know, even when you're doing subtraction here, the addition is super simple, right? But if you're doing subtraction, now when you borrow, you're not just borrowing 10, you're not just borrowing 1, you're borrowing 16, okay? And so that's really 1 0 in hex, right? So it just gets a little bit complicated. I'm more concerned that you understand how the binary works because that's what is going on in your PC, your processor, okay? There's also BCD arithmetic. And so the easiest way to do that is just convert them into decimal and do the math, okay? So I'm not gonna make you do the BCD arithmetic either, okay? So let's go ahead and talk about arithmetic circuits. What if you wanted to do this stuff with logic gates? How could you do it? Okay, and this is just these are a couple of the truth tables we've already looked at, right? So the first one we're going to look at is called the half adder. And if you're taking notes, which I hope you are, I would make a note that this is going to be either the half adder or the full adder is going to be required on the exam for you to redraw, okay? So the half adder is really only good for one column, and that's the least significant bit column, okay? So it says, you know, you have an exclusive OR to get your summation out because, you know, of the way that the ones and zeros work with binary arithmetic. And then the carry out is over here with the AND gate, okay? And so this will perform the half adder function where you have the summation and you have the carry out. What this does not allow is for a carry in to happen. So that's why it's only allowed to be in the least significant bit, okay? It says the half adder can also be implemented using NOR gates and one AND gate. And so, you know, either way, if you have this one or if you have this one, they will accomplish the same thing, okay? So a full adder is what you use for all of the other bits, okay? And so this provides for a carry input. So now you can have, you know, 1 plus 1 plus 1 potentially. It says the summation output is high when the 3-bit input is odd. Yeah, it's essentially an even parity generator if you want to describe it like that. And it says that the carry out is high when any 2 inputs are high, okay? So it looks like this. This is a full adder summation. All right, this is just the summation. So this is the full adder summation. And essentially, like I said, it's just, you can see here, it's just a bunch of, you're exclusive ORing everything together, which we know from the previous chapters is an even parity generator, right? If you just exclusive OR all inputs together. And so essentially that's what happens. But that's valid based on what we just saw with all the math I just did on the board, okay? And so here's the carry out function. You AND these things together and then you OR them at the end. So any one of these can trigger the carry out to be high, okay? So full adder summation, full adder carry out function. Right? And then back here, just to reiterate, the half adder is only for the least significant bit. The full adder, with its summation and carry out, is good for all, okay? All the other bits. Okay, and so, you know, if you wanted to just use the 3 inputs here, this is what the complete full adder looks like. Okay, then we talk about the VHDL description of it. Now, here we go into, you know, we're starting to think bigger picture now with the block diagram, where the half adder just takes into account the A and B and gives you a summation and carry out, whereas the full adder here in the block diagram, now we account for this carry in measure here. And we could add these together if you wanted a 4-bit binary adder, you know. I was about to say it looks just like when you put flip-flops together, but we haven't talked about flip-flops yet, so that's not going to make any sense. So here's the half adder down at the least significant bit here. The carry out becomes the carry in of the next set of bits, the A1 and the B1. So you add all those together, you have a summation out, and then that carry out becomes the carry in of the next. Okay, and it just keeps going on like that. You could have an 8-bit binary adder, a 16-bit binary adder, and obviously, this is not a gate or an IC chip. We're just saying that, you know, inside the box, so to speak, that's where the digital circuit is. Okay, and there's an IC for that. I'm not going to quiz you over what these ICs are. Okay, let's see here. All right. So I do want to talk about this right here. So this idea of the fast look-ahead carry, all right, says it evaluates the 4 low-order inputs. The high-order bits added at the same time eliminates waiting for propagation ripple, okay? We haven't really talked about propagation ripple that much because it hasn't been a factor, okay? But think about this. To get the final answer, not only do you have to have A's, all the A's and B's up here, but this one, like this one right here, this second column is dependent on this one. So what we mean by propagation ripple is propagation delay is how long does it take for a signal to go from the input to get processed and then to the output, okay, to change the output, so to speak. So that takes a little bit of time. Then that carry-in comes over here, and it takes time to process this one. And then this one has a carry-out. So that's what we mean by propagation ripple. Because essentially, this propagation delay plus this one, plus this one, plus this one, if you have enough bits strung together like this, that's a pretty good stretch of time, you know, when we're trying to be very, very quick, okay? So to eliminate that, this is what happens. So before anything reaches these adders, we have this fast look-ahead carry that kind of gets a map of what's going to be displayed, and it saves a little bit of time, okay? So evaluates the 4 low-order inputs, high-order bits added at the same time, and eliminates the waiting for the propagation delay, propagation ripple. Okay. Let's see here. I don't know how much more I want to say about this. There's some really neat applications that Kleitz goes into. Okay. And I'm not even going to do a whole lot with the arithmetic logic units, but I just want you to see how powerful they are and what all they can be used for. I keep losing my place here. Here we go. Okay, so it's a multi-purpose device that can be used for, geez, there's a whole list. You have to look at the table to even see what the selection is. You have 4 function select bits here. So that means it goes from 0000 to 1111. So there are 16 separate functions that this thing can perform, all right? And it just depends on what the function you have selected, depends on what happens with these 2 binary strings, okay? And here's the table. So depending on the mode select that you have, you could either have it in logic functionality or you could have it in arithmetic operations, okay? So if we go back here, we've got our output F, we've got our input A and input B. We have our carry-in, potentially from another arithmetic logic unit. We have our mode control, whether or not we're in arithmetic, where we're going to actually do some mathematics, or are we talking about our things true and false and using the logic sector. So, you know, really, there's an extra bit here that controls that, right? Because when we're doing the arithmetic, that's going to have its own set of 4. And then when we're doing logic, it's going to have its own set of 4 bits. And so that's why you see here, we've got 32 of these functions all on the same table, okay? And that's because, you can see that the mode is high here or the mode is low. And so, it just depends on what you have chosen. You can get any of these functions. And look at all these logic gates, right? Here's an exclusive OR, right? When you're high, low, low, high, and you're in mode logic, that is an exclusive NOR function, okay? All right. And there's a section in the book that talks about how you can actually create your own symbol in Quartus, for that matter. You can determine all the inputs, you can determine all the outputs, and essentially create yourself a little IC chip. Okay, and they call it a macro function. Okay, we've already done this too, right? Where we've pulled off the bus line, and this is how you name the bus lines individually, right? A sub 0 with the brackets and all that good stuff. But this is using a 74283, which it's a 4-bit adder. Let's see, and this is macro functions, VHDL, BCD, LPM. All right. Okay, so just to recap here. So the binary arithmetic functions of addition, subtraction, multiplication, division can be performed bit by bit using several of the same rules of regular base 10 arithmetic, and we saw that. 2's complement representation of binary numbers is commonly used by computer systems for representing positive and negative numbers. And 2's complement arithmetic simplifies the process of subtraction of binary numbers. That it does. Don't worry about this part because I'm not going to test you on it unless you just want to. When I say don't worry about it, I'm not saying that it's not important at all. If you want to learn more about it, then read that section out of your book. Okay. Same thing with when you're performing BCD mathematics. So binary adders can be used building simple logic circuits, combinational logic circuits like we know. You can also use IC chips. And it says a half adder is required for addition of the least significant bits, and then a full adder is required for all of the more significant bits. And arithmetic logic units are multi-purpose ICs capable of providing several different arithmetic and logic functions depending on how you have the mode set. Okay. So any questions on this? I realize it's pretty dry. Do you want me to do any other, I'll type this in here. Do you want me to do any other calculations, such as binary subtraction or binary multiplication, division, etc.? I said, do you want M to do any other? But it's me. Do you want me to do any other calculations? Because I could do a few more if you want me to, or... So David says, not on this. When do you think our grades will be in for the exams? Well, it's 2:30 now, and my wife and kids, I heard them about a half hour ago. I heard them take off for my parents' house to swim, so I have undivided time now. Here's the thing, though. I also have the 111 tests to grade, and those are going to take me more time because, as you know, if you typed in the wrong answer, like all 5 points disappeared, right? And so, as I said before in our 111 Zoom lecture, that one's going to take me some time to grade. So it's a matter of, which one do you want done first to some degree. But the 111 lab is going to take me a lot longer. So I don't know. I'm going to grade one or the two, or it'd be great if I could get them both graded today. But I know the 111 one's going to take me a while because I'm going to try my best to do as much partial credit as possible, okay? So, I don't know. My hope is for tonight, but it could be tomorrow. Tomorrow, I just have 111 in the afternoon. So anything I don't get done tonight, I will do in the morning tomorrow. So my goal is to have both of them graded by 1 o'clock tomorrow at class, and that way we can talk about it. And I can do the problems on the board. I'm going to go through each one, okay? Anybody else? If not, then I will get to work on grading. And you all have a nice day. It's actually pretty nice outside, I think, at least here. I don't know where all you are right now, but at least here south of Indianapolis, it's all right. So enjoy the day. I'll try my best to get all this done tonight, but give me a break if I can't get it done until the morning, okay? All right. You guys are all free to go. I appreciate you guys coming in and participating and giving me some feedback. And I will talk to you later.